Welcome back to the Deep Dive. Today, we are attempting something a little ambitious.
Just a little.
We're going to try and draw a straight line through, roughly 55 years of computing history?
Yeah.
We have a stack of notes here from the CS330 course, simply titled Class 2. But honestly, the content is anything but simple. We are going to cover everything from the chaotic leaderboard of modern programming languages in 2026, all the way back to this blue metal box from 1971 that didn't even have a microchip.
It is a massive span of time, but what's fascinating to me is that the core problems haven't actually changed that much.
Really?
Yeah. Whether you are looking at the absolute bleeding edge of AI code generation, which, we will get to, or hand-toggling switches on some vintage console, we are still trying to answer the same question. How do we talk to the machine without losing our minds?
That's the mission today. We aren't just reading a syllabus, we are digging into the philosophy of language design. We need to figure out what makes a programming language good, what makes it obsolete, and why, despite having tools like ChatGPT and Claude to write code for us, we still need to understand how the sausage is made.
Yes. We have to move beyond how do I type a tag in HTML to understanding Turing completeness and the architecture of logic itself.
Because the tools will always change.
The tools always change, but if you understand the design, you can survive.
Okay, so let's orient ourselves. It's January 2026. The TIOBE index just dropped their annual analysis. For anyone who doesn't follow this religiously, TIOBE basically ranks language popularity based on search engine volume, engineer demand.
Right. It's a proxy for what people are actually using and asking about.
And the headline for 2025 is C#.
Programming language of the year, again.
Again. It won 2 years ago as well.
Oh, it did.
Which feels surprising, right? I feel like 10 years ago, C# was just that corporate language you use if you work at a bank.
Oh, absolutely. It felt very enclosed in the Microsoft ecosystem.
Cool.
And that's exactly why it's winning now. The analysis points out that C# pulled off a maneuver that is, incredibly rare in tech.
What's that?
It successfully reinvented itself. It went from being this proprietary, Windows-only walled garden to a genuinely open-source, cross-platform powerhouse.
It's a lesson in adaptability, then.
Totally. If C# hadn't moved to .NET Core and embraced Linux, it would probably be sitting where Delphi is right now.
Loved by a few, forgotten by most.
Exactly. Adapt or die.
But looking further down the list, it seems like a battlefield. You have C and C plus constantly swapping places in the top 3.
Always.
And C is still holding the crown for small embedded systems. Why hasn't that changed? I mean, everyone has been screaming that Rust is the C killer for years now.
Yeah, and look where Rust is, number 13.
13. That's respectable, but...
It's not a takeover. The issue with embedded systems, we're talking about the code inside your microwave, your car's braking system, a pacemaker.
Right.
Is that C is good enough, and the switching cost is astronomical.
So it's just inertia.
It's massive inertia. C lets you manipulate memory in a way that is, let's say, dangerous, but incredibly efficient.
And Rust adds safety rails.
Rust offers safety. It stops you from shooting yourself in the foot. But that safety comes with a learning curve and, compiler overhead that the embedded market is just resisting.
Okay, that makes sense. But the real shocker on this list for me is Perl.
Perl, yes.
Perl, as in the duct tape of the internet, Perl, the language that looks like line noise when you read it.
The very same. It jumped from position 32 back up to number 11.
That is baffling. Is there a Perl renaissance happening that I missed?
It's less of a renaissance and more of a zombie apocalypse situation.
Okay, explain.
There is so much legacy infrastructure out there running on Perl scripts written in the late 90s. And as companies try to modernize or move to the cloud, they're realizing they can't just delete those files, they have to maintain them.
So demand is spiking just to keep the lights on.
Exactly. It's hilarious and terrifying.
Meanwhile, the cool kids are suffering. Go and Ruby, you're dropping.
Ruby fell out of the top 20 entirely, which is harsh.
That feels really harsh.
It's the hype cycle in action. Ruby was the darling of the web startup world for a decade. But now, if you're a startup, you're probably using TypeScript or Python.
The ecosystem moved on.
It moved on. And this really highlights why we are doing this deep dive. If you just learn syntax, if you just learn how to write Ruby, you are betting your career on a fashion trend.
But if you learn language design concepts,
you can survive when the rankings quit.
So to understand design, the CS330 course throws students into the deep end. Not with a modern language, But with the Kenbai 1.
The Kenback 1, 1971. This is arguably the first personal computer, predating the Apple I, the Altair.
I'm looking at the photo from the notes. It doesn't look like a computer. It looks like a piece of lab equipment.
It does. A blue metal box.
There's no keyboard. There's no monitor.
No screen, no mouse. You have a row of lights, LEDs for output, and a row of push buttons for input. That is your entire interface.
And under the hood, what's going on in there?
It's fascinating because it doesn't even have a microprocessor. The CPU hadn't really been productized yet.
So what's doing the thinking?
This thing was built with TTL logic chips transistor logic. Basically, a bunch of discrete logic gates wired together to act like a computer. And it had 256 bytes of memory.
256 bytes. We need to pause on that.
Yes.
A single icon on my desktop is probably, what, 20 kilobytes?
At least. We were talking about a tiny fraction of that.
Wow.
256 individual slots to hold information. And here's the constraint that just breaks people's brains. That 256 bytes has to hold your data and your program instructions.
They share the same space.
They share the same space. If you write a program that is too long, you overwrite your own variables.
That is incredibly claustrophobic. Okay, so walk me through the programming experience. I want to add 2 plus 2. What do I do?
Well, you can't type anything.
All right.
You are programming in pure machine language. You are acting as the compiler. So first, you need to know the opcode, the operation code for addition. Let's say, hypothetically, the instruction for ADD is the number 004. You have to convert that to octal, base 8.
Why octal?
It was just easier to represent on the buttons available at the time. So you look up the code, you toggle the buttons on the front panel to represent 004.
Okay, so I'm physically pressing buttons.
Physically. Then you toggle the buttons to say where in memory that instruction goes. Then you press store.
One instruction down.
One down. Then you toggle the buttons for the number 2, store that in a data slot. Then you toggle the instruction to load that number. It's a manual physical process of entering numbers into memory addresses one by one.
You are literally speaking the hardware's native tongue. There's no interpreter.
No syntax error warning.
No.
None. If you type the code for ADD, but you make a mistake and type the code for JUMP, the machine will just jump. It doesn't know what you meant. It only knows what you entered.
That's bare metal in the truest sense.
The truest.
So the notes mention a specific challenge the instructor, Dave Reed, undertook. He wanted to program a game called Dr. Nim on this machine.
Right. Dr. Nim is a classic strategy game from the 60s. It's a subtraction game.
You start with 15 marbles, and you can take 1, 2, or 3.
And the goal is to force the other player to take the last one.
It's a solved mathematical game. If you play perfectly, you can always win.
Correct. The logic involves modular arithmetic, basically keeping the marble count at multiples of 4 plus 1. So Dave wanted the Kenback to play as the computer opponent.
Now, in Python, this is like 5 lines of code. You just use the percent modulo operator.
Yeah, but the Kenback doesn't have a modulo operator.
Of course not.
It barely has subtraction. Dave had to write the logic using raw jumps and bit manipulations. The resulting code was 113 bytes long.
It's nearly half the machine's memory.
Half the memory. For this simple game, and looking at the code, it's just a wall of octal numbers. 004, 123, 007. It is completely opaque.
If you looked at it a week later, you would have no idea what it did.
Absolutely none. And this is where the lesson pivots. To solve this readability nightmare, Dave created a tool. He built a language called Kblang.
This is the hero of the story, Kblang.
It's a custom language designed specifically for the Kenback, and it introduces the concept of abstraction.
So instead of memorizing that 0241, shifts a bit to the left.
Kblang lets you write. Bit shift B left 4.
It's infinitely better. It actually reads like a sentence.
Instead of remembering that memory address 150 is where the game starts, you can simply write label new game.
So the software, the compiler, does the grunt work of translating that back into the machine code.
Exactly. It translates new game into address 150 and bit shift into 0241.
This brings up a philosophical point mentioned in the notes. There's a quote from John von Neumann, one of the fathers of computing. He famously asked, why would you want more than a machine language?
It sounds so arrogant now, but you have to understand his perspective. He was a mathematician. To him, the machine was the numbers. Why put a layer of fluff between you and the truth?
But then you have Edsger Dijkstra, who countered that view. He said, the purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise.
I love that phrase. A new semantic level. It's perfect.
It's profound. Von Neumann thought abstraction was dumbing it down. Dijkstra argued that abstraction is clearing the clutter.
Right.
When you use cabling, you aren't worrying about which wire is carrying the signal. You're worrying about the logic of the game. If marbles equals 1, stop. That is a higher level of precision because you are describing the intent, not the implementation.
So cabling is clearly better than octal for a human.
Yeah.
But this leads us to the theoretical meat of the course. How do we measure better?
Because I like it more isn't an engineering metric.
Exactly. The notes outline 4 specific criteria for evaluating any programming language: readability, writability, reliability, and cost.
These are the pillars. Let's break them down. Readability is first. This seems obvious. Can you read it? But it goes deeper. It's about cognitive decoding. When you look at K-Blang's bit shift B left 4, your brain instantly maps that to an action. When you look at 0241, your brain has to stop, look up a table, translate, and then map.
High readability reduces the mental load. Exactly. Then you've got writability. This is about how much friction the language puts in your way.
Does the language fight you?
Right. If I want to sort a list of names, a highly writable language like Python lets me say names, .sort. A language with poor writability might force me to manually swap memory pointers in a loop.
It's about expressiveness. Can I say a lot with a little?
Perfectly put. Then reliability. This is a big one, especially for those embedded systems we talked about.
This is about the language's ability to prevent you from crashing the system.
Yes, this brings in concepts like type checking. If I try to take the number 5 and add it to the word sandwich, a reliable language should stop me.
Before the program even runs.
It should say, hey, you can't do that. A less reliable language might just try it and give you garbage. Or a crash.
Or crash the car.
Or crash the car. Reliability also includes exception handling. When something unexpected happens, like the internet cuts out, does the program explode or does it catch the error and tell you connection lost?
Makes sense. The fourth one is cost. And this isn't just the price tag.
No, in fact, most languages today are free to download. This is about total cost of operation, or TCO. It includes the cost of training your engineers.
Right. If it takes 6 months to get a new hire up to speed, that's a cost.
It's a huge cost. It includes the cost of compiling. If your massive C++ project takes 4 hours to build every time you make a change, you are paying your engineers to sit around and wait.
And maintenance, I imagine.
Maintenance is huge. If the code is unreadable, fixing bugs takes 10 times longer. That is the hidden cost that kills projects.
There's one more specific term in the notes that ties into all of these: orthogonality. It sounds like geometry.
It's borrowed from math. In geometry, orthogonal lines meet at right angles. They are independent. In programming, orthogonality means consistency and independence of features.
Okay, give me a concrete example.
Think about the plus operator. In a highly orthogonal language, plus should work intuitively across different types. 1 plus 1 adds integers. 1.5 plus 1.5 adds floats. Hello, plus world concatenates strings?
The rule is plus combines things.
Exactly. Poor orthogonality is when the language has weird exceptions, like you can add integers with plus d, but to add floats, you must use the function addFloat.
It violates common sense. It forces you to memorize a list of gotchas.
Right. High orthogonality means you learn the rule once and it applies everywhere. It lowers the learning curve and increases writability because the language behaves predictably.
So we have these criteria. We use them to judge languages. But now we have to address the elephant in the room. The notes feature a roundtable discussion on an article titled, "Vibe Coding is Creating Brain-Dead Coders."
Vibe coding. It is the perfect term for 2026.
It really is. The premise is that developers are increasingly using AI LLMs like Claude or ChatGPT to route their code. And the author, Namanya Goel, argues this is rewiring our brains.
From deep understanding to instant gratification.
Yeah. He compares modern developers to gamblers.
That's a strong comparison.
It is. When you prompt an AI, you're pulling the lever on a slot machine. You get a chunk of code. You run it. If it works, jackpot.
And if it errors, you don't debug it. You just go back to the bot and say, that didn't work, fix it. You pull the lever again.
You hit regenerate response.
Exactly. You aren't engineering, you are vibe checking. And the danger, according to the article, is that we're creating a generation of junior developers who have never known anything else.
They look at code and they don't see logic. They just see output. This connects directly back to the can-bake one, doesn't it?
It's the antithesis. The whole reason this course forces students to study a 1971 machine is to break that vibe cycle.
You cannot vibe with octal code.
You cannot. You have to know exactly what 004 does.
The notes mention hard problems. Specifically, Project Euler Problem 15, lattice paths.
Right. It asks, in a 20 by 20 grid, starting top left and moving only right or down, how many possible routes are there to the bottom right corner?
And the trap is thinking you can just write a loop to count them all.
If you try to write a simple loop to count every path, a brute force approach, you will be waiting until the heat death of the universe.
The number is huge.
Yeah, over 137 billion. The computational complexity grows exponentially.
So if you ask an AI to solve this, and it gives you a brute force solution, and you don't understand the math?
You fail. You just burned a massive amount of electricity for nothing. To solve it, you need to understand combinatorics. You need to understand the algorithm, not just the syntax.
This is the brain-dead warning.
That's it. If we lose the ability to evaluate the language, to use those criteria of reliability and cost, we become slaves to the AI's output. We can't judge if the code is efficient. We only know if it runs.
And code that just runs often has hidden cost security holes, memory leaks.
Well, all the stuff that shows up 6 months later and brings the whole system down.
Right.
So the takeaway is, use the AI. It's a powerful tool, but you need to be the editor. You need to look at the AI's code and say, no, that's unreadable, refactor that, or that's going to cost us too much memory.
You can only do that if you understand the fundamentals.
Exactly. We have to do the hard work so we are smart enough to use the smart tools.
All right, let's wrap this up with the logistics. For the students listening, we have a syllabus to respect, and deadlines are approaching.
Right. The instructor, Dave, emphasizes that success is simple. Show up, keep an open mind, and do the work. Discussion leadership is a major part of the grade.
Which means you can't just sit in the back. And that brings us to the 2-1 rule for homework.
This is crucial. For every reading assignment, you must produce a minimum of 2 paragraphs of thoughts and 1 quiz question.
Do not forget the quiz question. It's an easy way to lose points. So what is on the docket?
For Monday, January 26th, you are reading chapters 1 and 2 of the compiler's textbook. You're going to start learning how to build that translator we talked about.
And for Friday,
January 30th, read chapter 3 of the textbook. But more importantly, read that article we just spent time on. Vibe coding is creating brain-dead coders.
prepare for the roundtable.
You need to have an opinion. Are you a gambler or are you an engineer?
Don't show up with generic vibes. Have a take. Here's the final thought I want to leave you with today. We started with C# being the language of the year, a language created by humans, for humans.
Right.
We talked about AI generating code. If AI eventually writes all our software, does language design even matter anymore? If no human ever sees the source code, does it matter if it's readable? Does it matter if it's orthogonal?
That is the million-dollar question. If the machine talks to the machine, maybe readable becomes obsolete.
Or maybe it matters more, because when the machines hallucinate, we are the only ones left to pull the plug.
I think I'd prefer to keep my hand on the plug, just in case.
Thanks for diving in with us. Read those chapters, toggle those switches, and we'll see you in the next deep dive.
See you there.